Parallel programming enhances computational efficiency by dividing tasks across multiple processors. It contrasts with sequential programming, which processes tasks one at a time. Understanding hardware architecture is crucial, as central processing units and graphics processing units handle parallel tasks differently. Platforms like AMD ROCm and CUDA facilitate parallel computing, while interfaces such as message passing interface and open multiprocessing enable effective communication and task management in parallel environments. Parallel programming involves dividing programs into concurrent subprograms executed on multiple processors. This requires coordination between processors, unlike traditional computing where a single processor executes instructions sequentially. Key platforms include AMD ROCm and CUDA, facilitating general-purpose computing on graphics processing units. Programming interfaces like message passing interface and open multiprocessing enable efficient parallel computing, enhancing performance and scalability. Traditional computing involves breaking programs into a series of instructions executed sequentially by a single processor, requiring no coordination. In contrast, parallel programming divides programs into concurrent subprograms executed on multiple processors. This requires coordination between processors, as each subprogram's instructions are executed in parallel, enhancing computational efficiency and speed. Hardware architecture defines the structure and organization of a computer's components. It includes the CPU, memory, storage, and input-output devices. Each component plays a crucial role in processing and executing instructions. Understanding hardware architecture is essential for optimizing performance and ensuring efficient communication between components, which is vital for both traditional and parallel computing systems. The CPU, or central processing unit, is the core processor in a computer, executing program instructions like arithmetic, logic, control, and input-output operations. It serves as the physical heart of the system, interfacing with peripheral devices and storage units to manage data flow and processing tasks efficiently. Central processing unit architectures vary to meet different computational needs. Complex instruction set. Computing offers complex addressing, while reduced instruction set computing simplifies with single-cycle instructions. Very long instruction. Word uses long, simple instructions. Vectorial architecture processes instructions as vectors, unlike numerical processing. Data flow architecture activates data, differing from other architectures. Each serves specific programming requirements, enhancing performance and efficiency. Emerging trends in CPU technology include increased core counts, energy efficiency, and integration of AI capabilities. Manufacturers are focusing on heterogeneous computing, combining different types of cores for optimized performance. Additionally, advancements in semiconductor technology are enabling smaller, more powerful processors, driving innovation in various applications from mobile devices to data centers. The CPU, or central processing unit, is evolving with trends like increased core counts and energy efficiency. Modern CPUs integrate AI capabilities, enhancing performance in data processing and machine learning tasks. These advancements are crucial for handling complex computations, setting the stage for the specialized processing power of GPUs. A graphics processing unit, GPU, accelerates graphics and image processing, crucial for rendering computer graphics. Its parallel structure makes it ideal for non-graphic calculations, especially embarrassingly parallel problems. This versatility has expanded its role beyond graphics, enhancing computational efficiency in various fields. Central processing units have a few cores with extensive cache, managing limited threads efficiently. Graphics processing units, with hundreds of cores, excel in handling thousands of threads, ideal for compute-intensive, data-parallel tasks. Graphics processing units dedicate more area to processing, making them suitable for programs with high arithmetic intensity, where the ratio of arithmetic to memory operations is significant. Central processing units are latency-oriented, featuring high clock frequencies, large caches, and sophisticated control systems for efficient sequential processing. In contrast, graphics processing units focus on throughput, with moderate clock frequencies, small caches, and numerous pipelined arithmetic logic units, excelling in parallel tasks. Central processing units excel in sequential tasks, while graphics processing units outperform in parallel processing, each being over 10 times faster in their respective domains. Graphics processing units, integral to video cards and gaming consoles, are designed for the 3D graphics pipeline, transforming applications through geometry and rasterization into images. Initially fixed, graphics processing units evolved with programmable shaders and general-purpose computing on graphics processing units' capabilities, enabling general-purpose computation beyond graphics. General-purpose computing on graphics processing units acts as a co-processor for compute-intensive tasks, leveraging high bandwidth between central processing unit and graphics processing unit. GPU performance is crucial for rendering complex graphics and executing parallel tasks efficiently. Key factors include core count, clock speed, and architecture. Optimizing these elements enhances rendering speed and computational power, crucial for gaming, simulations, and AI applications. Understanding these aspects helps in selecting the right GPU for specific needs, ensuring optimal performance and efficiency. GPU memory bandwidth quantifies the data transfer speed between a GPU and the system via buses like PCI Express or Thunderbolt. High bandwidth is crucial for performance, enabling rapid data movement essential for tasks like gaming and scientific simulations. Efficient bandwidth utilization ensures smoother graphics rendering and faster computational processes. The GPU pipeline begins with the CPU sending geometry data to the GPU. This data flows through stages: host interface, vertex processing, triangle setup, and fragment processing, ultimately producing a rendered image. The memory interface plays a crucial role in managing data flow and storage throughout this process. CUDA, a standard for native GPU code, offers extensive optimized libraries, but supports only NVIDIA devices with custom syntax. SHIP, from AMD, provides a common interface for both CUDA and ROCm devices, using standard C++ syntax. It mirrors CUDA closely, with a rapidly developing ecosystem, offering optimized libraries and tools from both AMD and NVIDIA. GPGPU leverages graphics hardware for non-graphic computations, ideal for data parallel applications. It enhances central processing unit performance by executing key computational kernels on the graphics processing unit, utilizing its numerous cores and high memory bandwidth. This integration is pivotal in high-performance computing, augmenting each node with graphics processing unit capabilities for efficient parallel processing. GPGPU leverages graphic hardware for non-graphic computations, ideal for data parallel applications. It acts as an accelerator in a heterogeneous system, with central processing units handling serial tasks and graphics processing units executing key computational kernels. This approach utilizes numerous cores and high memory bandwidth, enhancing performance in high-performance computing by augmenting each node with graphics processing units. Standard CPU code requires adaptation for GPU execution. Programmers must decompose problems using models like CUDA's hierarchical thread grid. Data transfers between CPU and GPU memory must be managed. Traditional languages need extensions or new languages. Post-porting, optimization is crucial for performance. Researchers are leveraging GPUs across diverse applications. General-purpose graphics processing units extend the capabilities of traditional graphics processing units by enabling them to perform non-graphics computations. This involves leveraging their parallel architecture to handle tasks typically managed by central processing units. By utilizing a large number of cores, general-purpose graphics processing units efficiently process data-intensive operations, making them ideal for scientific computing, machine learning, and other computationally demanding applications. Graphics processing units excel in parallel processing due to their numerous cores, offering significant speedups for tasks like matrix and vector operations. They efficiently handle floating-point operations, crucial for scientific computing and machine learning. Additionally, graphics processing units accelerate fields such as computer vision, natural language processing, cryptography, and bioinformatics, enhancing computational efficiency across diverse domains. While GPUs excel in parallel processing, they struggle with tasks needing sequential logic or complex data structures. Their limited memory and bandwidth can restrict data handling. Additionally, specialized programming languages and application programming interfaces are necessary, complicating development and increasing the learning curve for programmers. GPGPU programming offers diverse options. CUDA by NVIDIA allows C++ code execution on NVIDIA GPUs, with libraries for domains like deep learning. OpenCL, an open standard, supports multiple platforms, defining a C-like language for heterogeneous devices. Direct Compute, part of DirectX, enables GPGPU on Windows. Metal and Vulkan provide low-level GPU access on Apple and cross-platform devices, respectively. Parallel computing interfaces like Message Passing Interface, MPI, and Open Multiprocessing, OpenMP, are crucial for efficient data processing. Message Passing Interface facilitates communication between distributed systems, enhancing scalability. Open Multiprocessing, on the other hand, simplifies multi-threading in shared memory architectures, optimizing performance. Both interfaces are essential for leveraging the full potential of modern computing resources in various applications. MPI is a multi-process model for distributed memory systems requiring explicit communication management by the user. It excels in environments where processes do not share memory. OpenMP, on the other hand, is designed for shared memory systems, with implicit communication managed by the compiler, ideal for data parallel operations over loops. MPI, or Message Passing Interface, is a multi-process model with explicit communication, ideal for distributed memory systems. OpenMP, or Open Multiprocessing, is a multitasking model with implicit communication, suited for shared memory systems. MPI requires user-managed communication, while OpenMP relies on compiler management, focusing on data parallel operations over loops. Message Passing Interface excels in distributed memory systems, offering explicit communication and scalability beyond a node, but faces high latency and data placement challenges. Open Multiprocessing, ideal for shared memory, provides implicit communication, low latency, and dynamic load balancing, yet struggles with scalability beyond a node. Each model has unique strengths and limitations, making them complementary in parallel computing. Thank you for your attention. We hope this presentation has provided valuable insights into MPI and OpenMP, enhancing your understanding of parallel computing frameworks.